All right. So we talk about counting atoms, molecules, and ions in groups called moles. Okay, where a mole represents a count of 6.02 times 10 to the 23rd, at least three significant digits. Question is, how do we actually count atoms in the lab? Okay, we can't see them, so we have to do it indirectly. And so the concept of molar mass will help us do it, because the way we do it in the lab is we weigh things. From the weight or the mass, we can figure out how many moles we have. Okay, so first let's define the concept of a molar mass. The molar mass of a substance or a molecule or an ion is just the mass of 1 mole of that. So the molar mass of anything, anytime you say molar something, that's the mass of what, that corresponds to the value for 1 mole. So molar mass is the mass of 1 mole. So the unit for molar mass is grams per mole. You can write it like this, or grams per mole. You can write it like this. Okay. Now, by definition, molar mass of carbon-12. Okay, imagine you have a sample of carbon that every single one of those atoms happens to be carbon-12. You know in nature that's not what happens. You have a mixture of carbon-12, carbon-13. But if you can imagine you have a sample, if you can isolate all the carbon-12, separate them from carbon-13 and carbon-14, you just have a sample that's all carbon-12. Okay? So if you imagine a sample that's all carbon-12 and you have exactly 12 grams of that, okay, then that's the definition of a mole. If you could count the actual number of atoms in a sample that has exactly 12 grams of carbon, then that is Avogadro's number. So in other words, we're saying that if you have a mole of carbon-12 atoms, the mass of that sample is going to be exactly 12 grams. So the molar mass of carbon-12 is 12 grams per mole. So that's the standard. Prior to that, the standard was oxygen-16. It was defined to be exactly 16 grams. And prior to that, standard was hydrogen. A mole of hydrogen was defined to be exactly 1 gram. But the modern standard is based on carbon-12. A consequence of this definition are as follows. The consequences are as follows. If you have a mole of atomic mass units, okay, then, okay, to 3 significant digits, if you have 6.02 times 10 to the 23rd atomic mass units, that corresponds to a mass of 1 gram. Okay? If you have a mole of carbon, remember 1 mole of carbon-12, 1 carbon-12 atom, okay, 1 carbon-12 atom is exactly defined to have 12 atomic mass units. And so 1 carbon-12, 1 atom, okay, carbon-12, has 12 atomic mass units. 1 mole of atoms, 1 mole of carbon-12 atoms has a mass of exactly 12 grams. So you can see the correspondence there. It's the same number. So a consequence of that is that if you have the mass of an atom, ion, or molecule is X atomic units, then the molar mass is X grams per mole. Okay? So let's apply these ideas to this one right here. What's the mass of 1 carbon-12 atom in grams? So 1 carbon-12, okay, 1 mole of carbon-12 is equivalent to 12 grams exactly. And that's also equivalent to 6.02 times 10 to the 23rd atoms. Okay, so a mole of carbon-12 atoms has a mass of exactly 12 grams. So you can use these relationships to construct a conversion factor. So you can say, all right, if I want just 1 carbon-12 atom, then I can use a conversion factor. What am I looking for? Mass in grams. So this is my conversion factor right here. I'm going to say that has a 12 gram sample of carbon-12 will contain 6.02 times 10 to the 23rd carbon-12 atoms. So carbon-12 atoms cancel out. That gives you the mass of 1 carbon atom in grams. Okay? So that would give you how much? pull up my calculator here. 1 times 12 divided by 6.02 times 10 to the 23rd equals 1.99 times 10 to the negative 23rd grams. I'm using only 2 sig figs here, so I only keep, 3 sig figs, I only keep 3 sig figs here. Okay, this 12 right here is exact. Okay, or you could also say, another way of doing this is you can say, all right, 1 carbon 12 is exactly 12 atomic mass units. Okay, and I also know that 1 gram is equivalent to 6.02 times 10 to the 23rd atomic mass units. So another way I could solve this problem is I can say, okay, carbon 12 atom has a mass of 12 units times 1 gram is equivalent to 6.02 times 10 to the 23rd. Okay, 1.00 grams. I'm only doing 3 sig figs here. 1.00 grams is equivalent to 6.02 times 10 to the 23rd atomic mass units. So that's another way you can convert from atomic, that's one way you can convert atomic mass units to grams. Okay, so that gives you the same answer. That's going to be 1.99 times 10 to the negative 23rd grams. So you can see masses of atoms are very small. That's the reason why we count them in groups. Okay, so you can't weigh a single atom in the lab. You'll have to weigh moles of atoms in the lab. So what would be the mass of 1 mole of protons? Well, what's the mass of 1 proton? If you remember from before, it's 1.00 atomic mass units. Okay, so 1.00 atomic mass units times, you can just convert it using the relationship that 1 gram is 6.02 times 10 to the 23rd atomic mass units. By the way, you can use AMU or U for atomic mass units. Okay, so that gives you the mass of a proton, which is let's see, 1 divided by 6.02 times 10 to the 23rd. So that's 1.66 times 10 to the negative 24. So each proton has that mass, about 1.7 times 10 to the negative 24 grams. And so does each neutron, approximately, to 3 sig figs. Okay? Now, what about isotopes? Molar mass of specific isotopes, you're not going to be able to find that in a simple periodic table. You're going to have to look it up. So, for example, carbon-13, if you look it up, you'll find it to be, the mass of 1 carbon-13 is 13.003354826. Okay? And where can you find something like that? You can go to a website like webelements.com. If you remember, you can look up the mass of your isotopes. So if you click on carbon here, you can see that, and over on the left side, you look at the isotopic information, nuclear properties, isotopes. And you can see right here, the mass of carbon-12 is exactly 12 grams, 12 atomic mass units. The mass of carbon-13 is 13.003354838. Okay? So that means 1 mole of carbon-12 is going to weigh exactly 12 grams. 1 mole of carbon-13 will weigh 13.003354838 grams. Alright, so that means the molar mass of carbon-13 is the same number, but the unit is grams per mole. The mass of a single atom is the same number, except that you put a U there. So you can see then that to the nearest gram, okay, the numerical value of your of your molar mass is equal to the mass number. Okay, just like the average, the mass of the atom would be equivalent to the mass number numerically. So if you're asked for the molar mass of an element and we don't specify the isotope, for example, if I ask you what's the molar mass of carbon, you're not going to give me exactly 12, because when I say just carbon, that means if I just say carbon, what I mean is a naturally occurring sample of carbon, which may have some carbon 12, mostly carbon 12, some carbon 13. So it's not going to be exactly 12. So you look at your periodic table, and there's a number there that you find, that's the average atomic mass. So if the average mass of carbon atoms is 12.01 atomic mass units, okay, so 12.01 atomic mass units is the average for a naturally occurring sample of carbon, then the molar mass is 12.01 grams per mole. Okay, so atomic mass units tell you from the periodic table, tells you the average mass of atoms in a naturally occurring sample in atomic mass units. But that same number, if you put a different unit to it, attach a different unit, grams per mole, that gives you the molar mass. So the molar mass of carbon is carbon 12. Here you have nitrogen. The number next to nitrogen there is 14.01. That means if you have a mole of nitrogen atoms in nature, it's going to weigh 14.01 grams. Okay, so the molar mass of nitrogen is 14.01 grams per mole. Okay. What about molar mass of ions? If I were to ask you, what's the molar mass of oxide ions? O with a -2 charge. Well, molar mass of oxygen atoms is, according to this, 16.00 grams per mole. Well, what about oxide ions? Well, you have to realize that electrons contribute very little to the mass of the atom. Remember, each proton is about 2,000 times heavier than an electron. So it's still going to be, for practical purposes, the same number. So it's going to be 16. In the case of oxygen and oxide, they're going to have the same molar mass. 16.00 grams per mole. Okay? When we do use molar masses from the periodic table, make sure you use 4 significant digits. For most practical calculations, we have to use 4 significant digits. Don't just round it up to the nearest whole number, okay? So for most of these cases, you go to the second decimal place. For oxygen, you have to go to the third decimal place to get 4 significant digits. It's 1.008 right here. Oxygen is 1.008. Okay. So what about a mole of molecules? What would be the mass of a mole of molecules? The molar mass of molecules, you just look at the formula and just add up the molar masses of each atom indicated in the formula. So H2O, for example, water, a mole of water molecules will have, to say 1 mole of H2O contains 2 moles of hydrogen. So that means 2 times 1.008 grams. Okay. And it's going to have 1 mole of oxygen. Okay, so there's 1 there. 1 mole of oxygen. So 1 times 16.00 grams. That's a total of, if you add that, you're going to get 18.02 grams. So you say then that 1 mole of water molecules will weigh 18.02 grams. So you say the molar mass of H2O molecules is 18.02 grams per mole. Okay? So just add up all the molar masses given in the formula. Now, some synonyms you might encounter when dealing with molar masses. These are all things that have basically the same numerical value: atomic weight, atomic mass, gram atomic weight, gram atomic mass. So those all have the same numerical value as molar mass. So you might see them in older textbooks, or so you just need to be familiar with them. Okay. So they're numerically identical. These are the numbers that you find on the periodic table. Okay. So the atomic weight, okay, is actually a relative number. It's a unitless number. Atomic mass is the mass of the atom, so it's given in atomic mass units, or U, or you can use the symbol D for it, for Dalton. So one atomic mass unit is 1 Dalton. Or and then the gram atomic weight and the gram atomic mass, that's just the mass of 1 mole of atoms in grams. This is a really old way of referring to molar mass, okay, or molar. We use, chemists used to interchange mass and weight all the time. So atomic weight, gram atomic weight would be the weight in grams of a mole of atoms. Similarly, you might encounter terms like molecular mass, molecular weight, gram molecular weight, formula mass, formula weight, gram formula mass. All of those terms numerically mean the same thing. They have the same numerical value as the molar mass. All right, so now that we know that how much a mole weighs, okay, so remember, what did we say a mole of water weighs? 18.02 grams per mole, right? In an earlier slide. So you say then that, okay, 1 mole of water, if I have 1 mole of water, what would be the mass? 18.02 grams. If I have twice as many moles, what do I expect? I expect twice as much mass. It's going to be 2 times 18.02 grams. If I have 3 moles of water, I expect 3 times as much mass, 3 times 18.02 grams. Okay? In other words, however many moles you have, if you represent that by the letter N, you multiply that by the mass per mole. So M sub M here is our symbol for molar mass. So you have grams multiplied by the actual grams per mole. That would give you, you have number of moles. You multiply that by the grams per mole. That will give you the mass in grams. So what's the mass of 2 moles of water? You can say 2 moles times whatever the mass of 1 mole is. It's like saying, how much does 2 gallons of gasoline cost? Well, the number of gallons times however much the 1 gallon costs, right? What's the number of gallons times cost per gallon? So same thing here. You say 2 moles of H2O multiplied by the molar mass, which is 18.02 grams for 1 mole of H2O. So you can see that moles of H2O cancel out. Okay, so number of moles multiplied by the molar mass. If you prefer to use a formula, you can say the mass is equal to number of moles times the molar mass. So that's what we did here when we did this picket fence calculation. This is the number of moles multiplied by the molar mass. Molar mass is this one right here. Okay? So you can reverse the process. If you go to the lab and you weighed out a sample of water and your balance tells you this sample of water weighs 36.04 grams, how do we figure out how many molecules of water we have? Well, if you know the mass, you want to figure out moles, then you just go backward. Instead of multiplying by molar mass, you divide by the molar mass. So I'm going to say then, well, look at this. That's 36. I know a mole of water is 18, right? So that's about 2 moles of water. And here's how you do it. You say 36.04 grams of H2O times 1 mole of H2O has a mass of 18.02 grams of H2O. So grams H2O cancel out. So 36 divided by 18 Okay, so here 36, the mass is 36. You divide by the molar mass, which is 18, that gives you moles. So you can think of it this way: number of moles times molar mass. Okay, so you say mass equals number of moles times molar mass. If I want to solve for number of moles, I can say number of moles is mass divided by the molar mass. And that essentially is what we did here. Mass is this one. You divide by the molar mass, which is 18.02. So if you did that calculation, 36.04 divided by 18.02, that should give you 2.000 moles of H2O. Not just 2, it's 2.000. Why? You have 4 sig figs here, 4 sig figs here. That one there is an exact number per mole of water. Okay, so that's the number of molecules. The number would be 2 moles. Now you might say, shouldn't I multiply that by Avogadro's number? Sure, if you want to, no problem. If you want to change that to an actual count, then you can say 2.000 moles of H2O. You can change that to an actual count. You say 1 mole of H2O would have 6.02 times 10. I probably need an extra digit here, so I'm going to use 6.022 times 10 to the 23rd molecules of H2O. Okay, so some teachers expect you to do it that way. If they're asking for how many, they want an answer in actual count, but I don't. If you give, because a mole is just another way of counting. So if I say how many, I don't mind if you give me how many molecules or how many moles. Okay, but there's some that are a little bit more picky. If they say how many, you have to give them the actual individual count rather than the mole count. As far as I'm concerned, if I ask you how many eggs, you can tell me 2 dozen or 24 eggs. It's the same thing. You're counting. All right, so in the lab, then we say we measure the mass of a pure substance and then divide it by the molar mass. That gives us the moles. Now, when we're dealing with liquids in the lab, we generally don't want to measure the mass of liquids as much as possible, because if you spill it, you'll be ruining an expensive piece of equipment. So what we do with liquids, especially if they're corrosive, is we just measure their volume instead of their mass. Okay? And then you can convert the volume to mass based on the density of the liquid. So for as long as you know what the density of the liquid is, you can convert its volume to density. So here's an example. The molar mass of carbon tetrachloride is 153.8 grams per mole. You can figure that out from your periodic table. Okay, and its density is 1.59 grams per mil. In other words, if I have a 1 milliliter sample of carbon tetrachloride, and if I were to weigh it, it's going to weigh 1.59 grams. So the question here is, how many moles of carbon tetrachloride are in a 200 ml sample? So if I just measured 200 mils, how many moles do I have? So you can just use a series of conversion factors here. So you're going to say 200 mils. Okay, I'm going to use the density to change it to grams. What's my density? 1.59 grams per mil. So 1.59 grams is equivalent to 1 mil. So I'm going to say multiply this by 1.59 grams in 1 milliliter. So milliliter cancels out. Okay, and now that I have my answer in grams, I can change it to moles. What's a mole? 1 mole of CCl4 is equivalent to 153.8 grams. Okay, so if I know my grams, I divide it by the molar mass. That would be 153.8 grams per mole. So you can see grams here will cancel out, and that gives me the answer in moles. Okay, think of it this way. What I did here is I converted milliliters to grams, and then what I did here is I changed my grams 2 moles. You can do this step by step, or you can chain these conversion factors in just one lengthy calculation if you want to do it that way. Okay, so of course this one right here, this is the using the factor label approach. If you want to use a formula, you can say, all right, density is mass over volume. So I multiply both sides by volume, I get my mass, right? So my mass is volume times density. My volume is 2.200 mils. And my density is 1.59 grams per mil. So same thing. That's that first step right there, changing milliliters to grams. And then you should already know how to do grams per mole, grams to moles. All right, so here's another example. If you have, let's say you have an experiment and it calls for 0.200 moles of ethanol, C2H5OH. The density of ethanol is given, and your molar mass is given. What volume of ethanol do we need? So I know the moles of ethanol. I need to change that to grams, okay? Once I know my grams, I can change that to mils using the density. So over here, I'm going to need the density here to get from grams to mils. So you need your density information here. What information do you need to go from moles to grams? You need molar mass. Okay? So to do that calculation, all you have to do is you can say, I can set it up as a picket fence here. 0.200 mole of ethanol. I'm just going to abbreviate ethanol like this, ETOH. It's a common abbreviation for ethanol. Okay. And then I need to change that to grams. So I need the molar mass, which is 46.07 grams per mole. So I need 1 mole down here and 46.07 grams per mole. So that allows me to cancel moles. Now that I have the answer in grams, I just change that to milliliters using density. What's my density? 0.785 grams per mil. So I can say density is 0.785 grams in 1 milliliter. And so that allows me to cancel grams. And so if you calculate that, you get 0.200 times 46.07 divided by 0.785. That gives you 11.7 milliliters. So what I do is I go to the lab, get a graduated cylinder, and fill it with ethanol up to the 11.7 milliliter mark, and that will give me the amount of chemical that I need for my experiment. Okay, so that's what you do if you know the volume. If you know the density and you're dealing with the liquid, it's preferable to measure the volume rather than the mass. Okay. Determining the elemental composition of a compound. This is one application. Okay, it's about time to quit. Go ahead. Yes, I think they're about ready to do this, the aqueous solutions lab next week. Our next PowerPoint is going to be on molarity on aqueous solution, so that should be just about enough time. So if you want to defer that, we could do a study session on Monday if they have last-minute questions about the test. Okay. All right. So, all right. Okay. Determining elemental composition of a compound. This is one application of the calculations that we've been doing today. you can use the molar mass, the calculation of molar masses, to determine the amount of element present in a compound. Let's say you were asked, what percentage of nitrogen dioxide is oxygen by mass? How much of that is actually oxygen, the element oxygen? And you could be asked, how much of oxygen can you get from 50 grams of NO2? So what you do is you go to your periodic table. So molar masses of nitrogen and oxygen are given there. So you say 1 mole of NO2 contains 1 mole of nitrogen, which is equivalent to 14.01 grams, and of nitrogen, and it has 2 moles of oxygen because it's NO2. So that's 2 times 16 grams of oxygen, so that's 32 grams of oxygen. Okay? So if you want the percentage of oxygen, well, what's the total? 14 plus 32, that gives you a total of 44.01 grams, right? Is that correct? 46.01 grams of NO2. So if you had 46.01 grams of NO2, you have a mole of NO2. Out of that, 32 will be oxygen. So you say the percentage of oxygen in NO2 is however many oxygen you have, 32.00 grams, out of the total, which is 46.01. So anytime you're comparing a part to the whole, divide the value for the part by the value for the whole, you get the fraction of it, and you multiply by 100% to get it, express that relationship as a percentage. And so you have 32.00 divided by 46.01. That gives you 6.6955. You multiply that by 100%. That's 69.55% oxygen. Okay? Now, how do you answer this next question? How much oxygen can you get from 50 grams? Well, it's 69, or that's about 70%, right? 70%, that means if you have 100 grams, you get 70 grams. So if you only have 50 grams, then half of 70 would be 35. So let's do that. You can say 69.55% of 50.0 grams is, in your calculator, you say 0.6955 times 50, that's 34.78 grams. Okay, so that's how much oxygen you can get from the 50 grams. Or if you prefer, you can do this using the picket fence approach. You can say 50.0 grams NO2. Okay, that will give you 32. The relationship of oxygen to NO2 is 32 to 46. So 32.00 grams oxygen, 46.01 grams NO2. So grams NO2 cancels out. Notice that this is really nothing more than 0.6955. Okay, this is 0.6955. So percentage times the actual mass will give you the mass of the element that's present in your compound. Okay? And so I think that's the end of this PowerPoint presentation. We'll continue with solutions and molarity next time.